So this is our second generation smart grid board. Our board is separated into 7 different segments. We have the solar panel, we have the breaker, and we have the 5 fault detection neighborhoods. The main difference between our board and the first generation smart grid board is the fact that theirs was entirely made out of analog circuits, while ours is mostly digital. We also have the voltage detection system, the solar panel, and the breaker neighborhoods that they do not incorporate. So here we have the fault detection neighborhoods. We have 5 neighborhoods, neighborhood right here, and down the center, and these 2 neighborhoods right on top. Each 5 neighborhoods are controlled by their own separate PICs. We also have 3 transformers, transformer 1, transformer 2, and transformer 3. As you can see, when I remove this transformer, it knocks out the 3 neighborhoods, and you'll be able to see it on the GUI. We can also pull out a single house and be displayed on the GUI as well. For these 2 neighborhoods, they're actually a little bit different from the other transformers. The transformer down here is dependent on the transformer up here, a branch transformer if you will. So when we pull out the transformer on this neighborhood, it knocks out both transformers and the neighborhoods that are powered by them. However, if we knock out this transformer, it only turns off the neighborhood on the bottom right here and completely independent from the neighborhood up here. This is our fault detection neighborhood. And we have Yu-Ming talking about the voltage detection system.
Here is the metering of the smart grid, so that the utility can keep eyes on the monitoring instead of sending people in the field. Looking at this portion of the window. So the first column here is reading the instantaneous power usage for each neighborhood here. And the second portion of the reading is the corresponding per unit reading for the voltage. Opening the hood, we can see underneath, different neighborhood is gonna bring the power into each PIC. And the PIC is gonna convert analog signal to digital signal. And then translate by the 4 to 7 decoder, bring to the ribbon wire, and the signal will come to in the front, which is the display 7 display. While the other portion of this reading system is the potentiometer we are setting up here to implement the peak and the low voltage usage for this neighborhood setup. So you can see right now it's 1.5, and once I turn up, you will see the power goes up instantaneously, all the way up to the highest power, which is almost 10. And this is the metering portion of the project. Now I'm gonna hand over to Evan, introducing the breaker neighborhood.
Okay, so what we have here is a different neighborhood. What separates this neighborhood from all the other ones is that it's being powered by 2 sources. We have one transformer here to indicate the source of 1, and another transformer over here indicates source 2. So when we look at the circuit breaker system, we see that the transformer is connected to the circuit breaker detector and also a shutoff switch, which can be controlled from over here. We have our little switches right here that control both sides. And so if current gets too much, there's too much current going into our transformer, the transformer will detect that and say the transformer will shut off automatically and edit and show up that it's being a fault. And so if we want to fix this fault, we can shut it off remotely over here, and we can see that it turned on red, and we can fix or find out whatever our problem is and then turn it back on. Now, as you can see earlier, that if I took out one transformer, it's being powered by 2, so it still has power. But if, say, we have a overloading current on both sides, we have a double fault and all the power goes out. And so, again, we would have to just turn off our power on both of them, fix our circuits, and instantly our power is back on because the circuit is fixed again. And now we can reset our circuit. All right, now we have Danny with our solar panel.
Okay, this is our solar panel neighborhood. It's independent from all the other neighborhoods. As you can see, the LED is a little dimmer. That reason for that is it's at a lower voltage. Everything else is powered at 5 volts. The solar panel powers at 3.2 volts. And the reason for that is it's a smaller scale. The solar panel is a mock neighborhood simulating the regenerative studies across the street. So we have our solar panel here, which is going to feed to a battery, and the battery is powering our LEDs. So right now we're simulating nighttime, and I will be simulating daytime using this flashlight. The way it works is we have our main solar panel that's going to be charging through the sun, and then we have a smaller solar panel that works as a solar cell sensor to do the logic with the voltage and send it to our PIC. But I'm not using the PIC, we are using the MSP430 as our microcontroller to control the logic of the servo, and hence going to move the servo back and forth. And I will simulate the sunset. Around. And again. And that's it. That's our solar panel neighborhood. For Smart Grid, here's Anthony.
Hi, Graphical User Interface, or GUI, was programmed in Visual Basic. Now, this allowed an easier and in-depth way of making the actual interface itself. As you can see here, we actually have individual buttons for each one of the houses. And underneath these buttons is actually the off version of the house. Now, the way it works is that the board actually sends in a binary value, which it gets through the main PIC, which sends through a serial port, into a USB port, into the computer, digits representing groups of houses on the board, with a 1 being the house is on and a 0 being the house is off. When it makes it to the GUI, it actually comes in as 4 bytes of hex, which is base 16, which is then read by the computer as decimal value. So then it goes through a long situation here, just cut through to here. Come on. It goes through a long situation where it actually translates the decimal value into binary. Once it's back into binary, each one of the bits is assigned to its group of houses. Take, for example, these group of houses, which are represented by the final group of 8 bits coming from the computer. They can be turned on individually or turned off individually. On the other hand, most of these digits are actually representing the transformers for neighborhoods. For example, this, which is neighborhood number 1, can be turned off by setting the main thing to 0. Now, the interesting thing here is that the main transformer for neighborhood number 1 also functions as a primary transformer for this neighborhood and this neighborhood. When the GUI is receiving data from the computer, it can then display the decimal value of the number sent on these 2 labels. This allows a basic representation of the board as it is currently going. As the board changes, it updates the GUI, and thus we get a visual representation of what is happening on the board, which can be viewed from a computer